Everyone, this is 11.3, which we'll be talking about the integral test and estimates of sums. Basically, this allows us to actually finally use calculus and our knowledge of integrals to figure out if certain series actually converge or diverge. So here, this is what the integral test is. There's a little bit of a technicality in the statement, but we'll discuss that with some key points here. And then finally, we'll do an example. And I won't actually prove the integral test to you, but I'll explain a little bit with the example why the integral test is true. So the integral test says suppose f is continuous, positive, and decreasing function on the interval 1 to infinity closed on 1, and let a sub n be f evaluated at n. So basically when the input of f is an integer or positive integer, so 1, 2, 3, and so on, then we consider that the sequence a sub n. So this actually makes a lot of sense because remember from what we saw from sequences from 11.1, that is, that a sequence is just a function over the natural numbers. So what we're doing is we're kind of letting f be the natural extension of some sequence that has these properties, and then from there we can actually see an association between the series over the terms of that sequence. So this is the integral test part. Then the series of a sub n from n equals 1 to infinity converges if and only if the integral from 1 to infinity, improper integral, from 1 to infinity of f of x dx converges. So if one converges, the other one converges and vice versa. Similarly, if one diverges, then the other one diverges. Okay, so there are some main technical points here. The first one that I think is most important is that the lower limit of the integral or the initial index of the series doesn't necessarily have to be 1. It could be 2 or 4 or 10, as long as it's not an infinite number. So if it's a finite number, even 100, it's fine. 100 seems large, but compared to infinity, it's pretty small. So no matter where you start, as long as they both start in the same thing, basically. It's kind of like we just be re-indexing for a different sequence. So there's not too big of a deal there. This next one is a little weird because I haven't seen too many examples of this, but it is actually true. F doesn't necessarily need to only be decreasing, it just needs to be decreasing overall, or ultimately decreasing, I guess is technically what it's called. Basically, past some x value, then it would be decreasing. So the function could weave in and out and have these alternations of increase, decrease, but then at some point, it must continuously be decreasing after that point. So that's kind of what that means there. But again, I wouldn't worry too much about the second point. And this one is actually pretty important. So here it says I'm using the acronym IT for integral test. So here, the integral test does not give the sum of the series. It only tests for convergence or divergence. So we'll be able to tell if, for example, in this example, we'll be able to tell if this series diverges or converges. We will not be able to tell what this sum actually is. To be honest, this one in particular is a pretty difficult one to show, and generally proofs of this are in more advanced math classes. I may bring up what this is because I think it's pretty cool. But right now, let's just not get carried away and let's focus on the integral test. So in order for me to use this example as a little bit of an explanation as far as why the integral test is true, well, what I'm going to do is I'm going to, well, of course, a sub n in this case is 1 over n squared. And what this compares to, well, this is our f of n. That's what the integral test statement kind of says here. Now, what that means is that f of x would then be 1 over x squared. So to find f of x, you just replace n's with x's, basically. And now notice, 1 over x squared, if you graph 1 over x squared, I'm just going to graph the right side. Looks like this. So notice it's positive, so all y values are above 0, and it's decreasing. Good. On the interval 1 to infinity is all we really care about. So I'm just going to list a few x values here. And I'm going to notice something. I'm going to try to use a different color here to show nice image. So what I'm going to notice is that if we create a estimation of an integral by rectangles, basically what we get is a Riemann sum. And in fact, what we can tell is that since this is a graph of f, we'll be able to actually tell that this sum is less than the integral. In fact, we'll be taking a look at this idea a little more when we get into estimates of sums. So this area here, we'll notice these lengths, the widths of these rectangles that is, are each 1. So since the lengths are 1, since the widths are 1, then we'll be multiplying those by the height to get, of course, the area of each of these. Now the height for the first one is just f of 1. But remember, f of 1, so this is f of 1. This height would be f of 2, and so on. So basically what we can say is the Riemann sum here will end up giving us this. It's the sum from n equals 1 to infinity of, well, just the area of these rectangles. Now the area of the first rectangle is going to be, again, 1 times f of 1, but f of 1, by definition here, is just, well, a sub 1. Similarly, the second one would be a2, and then a3, and then a4. So the red is really just the sequence that we're, not sequence, but the series that we're actually looking at. So this is actually in total this series here. And notice the area under the curve from 1 to infinity is actually going to be less than that. The only problem is that I'm not actually including this in the integral. So the area under the curve from 1 to infinity, so this kind of compares to the integral from 1 to infinity of 1 over x squared dx. So they're not necessarily the same, but they're close. Notice this is just a finite piece. So I'm not going to say that this is bigger than that or that's less than that, but what we can get an idea of is that if one converges, the other one converges and vice versa. And there actually is a way to get some type of inequality going where we can legitimately compare, and that'll actually be able to tell us which one converges when the other one converges. But that's really just me proving the integral test. So making a long story short, since the sum is really actually related to a Riemann sum of this integral, and they compare to each other, then when one converges, the other one converges and vice versa. So now what we can say is, well, let's take a look at this integral now, from 1 to infinity of 1 over x squared dx. And actually we've seen this before. If you take a look back at, I believe it was chapter 7.8, when we discussed improper integrals, and this actually converges. So just to show you, I guess, let me erase this and actually show that. Okay, great. So this is me applying the integral test, and what I'm going to do is solve this integral and show that it actually converges. So remember that we need to introduce t here. So the limit as t goes to infinity of the integral 1 to t of 1 over x squared dx. Now to antiderive 1 over x squared better, I'm going to write it as negative power and then apply the power rule. Remember how you apply the power rule, you add 1 to the power and then divide by the new power. So this is going to be the limit as t goes to infinity of x to the, let's see, negative 2 plus 1 is negative 1, and divide by negative 1. Okay, then we're going to evaluate this between 1 and t, and then take the limit of that. Perfect. Now, of course, this is really just negative 1 over x. So we'll evaluate that between 1 and t, and then take the limit as t goes to infinity of that. It's a little technical, of course, but we're almost there. And then we have limit as t goes to infinity of, plugging this in, we get negative 1 over t minus negative 1 over 1, which is just 1. In fact, minus negative 1 is really plus 1, so allow me to write that here. In fact, let me rearrange this as 1 minus 1 over t. That looks a little better to me. Perfect. And now we can see in the limit what happens with 1 over t goes to 0. So meaning that the limit actually just goes to 1, meaning the integral is 1. More importantly, the integral converges. So now, by the integral test, since the integral converges, then this implies that the series converges as well. So all it's able to tell us is that we have convergence. That's it. If it diverged, then the series diverged. Now the integral test is great because it actually gives you a solid answer. There's no scenario where it's inconclusive, because our test will actually be seen in chapter 11 that can possibly be inconclusive. The only problem though is that there's a pretty strict requirement to apply the integral test. That is, we have to have this function that has this specific thing going on. So we're going to take a look at a few more examples before we get to the estimates of sums. But that's really it for this section. So let's take a look at those examples right now. Right, so here we have these two examples where we want to determine if the following series actually converge or diverge. And of course, we'll be using the integral test. Now, to find out what f of x is, I don't think it's too bad. So here, f of x is going to be ln of x over x. And here, f of x is going to be 1 over the square root of x. That's the first step, really. And now what we can actually find out is ln of x over x decreasing is 1 over radical x decreasing. Now, of course, I'm going to do one example at a time. But as it turns out, ln of x over x is actually decreasing. You can actually find out by taking its first derivative and seeing where it's negative. Because remember, first derivative being negative means it's decreasing. So here, if you take its first derivative, you'd have to use, well, I guess the quotient rule. So f prime of x would be all over the bottom squared, derivative of the top, 1 over x, times regular of the bottom, x, so that's just 1, minus regular of the top, ln, times derivative of the bottom is just 1, so we have this. And in fact, well, we can see when x is 1 or greater, this is definitely negative. So let's kind of think for a second. When x is equal to 1, actually, we have 1 minus ln of 1. But notice, we're actually starting at 2, not at 1. So here, kind of what I said previously with the technical note I had for the integral test, it's not always 1. It could be something else. In this case, it's actually 2. So I made a mistake when I said when it's bigger than 1. When x is bigger than 2, this should be negative, but it actually isn't. Kind of weird. When x is 2, ln of 2 is 0.69, and 1 minus that is positive, and squaring anything in the denominator will always be positive. So this is actually positive when x is equal to 2. But if you plug in 3 or anything higher than that, then this is certainly going to be negative. And the reason I know that is, of course, ln of e is equal to 1. And since ln is increasing, what this implies is that ln of x is bigger than 1 only when x is bigger than e. And since 3 is the first integer that's bigger than e, because e is 2.7, then plugging in any number beyond 3 will be decreasing. So this is actually an example of the second note I showed, where it doesn't have to be always decreasing, just decreasing overall. So past x equals 3, it actually is decreasing. So it's decreasing. Are they all positive? Yes, they are. In fact, if you plug in ln of 2, so start with 2, ln of 2 is 0.69 over 2. That's obviously positive. Positive over positive is positive. And anything beyond that would also be positive. Good, so I think that makes sense. So it's positive, decreasing, and of course continuous, because each ln of x and x is continuous beyond x equals 2. So now, finally, what we're going to do is the integral part. We'll find the improper integral from 2 to infinity of this function. So I've cleaned that up, so here we go. So we have the integral from 2 to infinity now of ln of x over x dx. Now, can we actually integrate this? This, I think, is actually really hard to integrate, so we'd have to use some type of comparison. I'm trying to think what we can use to compare this with. Well, I know ln of x is, let me think. I know ln of x is less than x. I'm trying to think if that would work. I think that actually works. But I want it to be greater than something. I'm trying to think for a second here. Well, we know ln of x is bigger than 1. I think that actually works. So ln of x is bigger than 1, not beyond 2, But we can write it like this. We can write this as the integral from 2 to 3 of ln of x dx. Sorry for the slight pause. I'm just honestly thinking about how we would attack this problem just so we can understand and think about thought process here. So I'm splitting it up into two things. This is finite, so we actually don't care about any finite piece because this always converges because it's a finite number. It's just a finite area under the curve. This, maybe not so much. So now we really want to focus on this integral here. So if you take a look at the integral, so let me just write it separately. The integral from 3 to infinity of ln of x. Remember that ln of x, like we said earlier, is bigger than 1 when x is bigger than 3. So we can actually say that this is going to be bigger than or equal to the integral from 3 to infinity of 1 over x dx. Because since ln of x is bigger than 1, we can say ln of x over x is bigger than 1 over x. Good. And now this, actually we've seen this, we've again, going back to 7.8, if you remember I believe I called it p integral, where we have 1 over x to a power, 1 over a power of x. If the power of x was 1 or less, and you're going from a finite number to infinity, then the integral actually diverges. So this diverges, but again, just to show you, we can take the antiderivative. So it's ln of x evaluated between 3 and infinity, and when you plug that in directly, you just get, well, infinity. Now I know I'm doing this not super technical, and I'm not using limits, but if you replace infinity with t and then take the limit as t goes to infinity, you get ln of t minus 3 minus ln of 3. ln of 3 is finite, so don't worry about it. ln of t goes to infinity as t goes to infinity. So basically what we get overall is that the integral diverges. Perfect. So since the integral diverges, that means the series must diverge as well by the integral test. Perfect. So I know that was a lot. Number 2 is going to be a little less crazy. It's more tamed. But I'm going to erase this and write a result over there. All right, perfect. So here's our result we just got. The integral diverges, so by the integral test, the series diverges as well. Great. So now for this one, well, let's see. So we want to take the integral from 1 to infinity of 1 over radical x. I'm going to write that as a power x to the negative 1/2 dx. Now, of course, 1 over radical x is positive because we're plugging in numbers from 1 to infinity for x. So you won't get a negative number out of that square root. At the same time, radical x increases, so 1 over radical x decreases. If you want to do the derivative thing, you can, but you'll see it definitely decreases. So these are good things to check because it allows you to know if you can actually apply the integral test or not. Okay, so now that we know that, or you could, of course, just graph, but it depends on what you're able to do under the circumstances. Anyway, so now if we antiderive this, we'll get, remember how we antiderive a power of x, you add 1 to the power, divide by the new power. So if we add 1 to negative 1/2, we get positive 1/2. And if we divide by 1/2, we're just multiplying by 2. And then we want to evaluate this between 1 and infinity. And again, I'm not really being technical here. I really should say evaluating between 1 and t, and then take the limit as t goes to infinity. So in fact, I'll actually write that here. So we want to take the limit as t goes to infinity of, plug in the top one, which should be t. So it's 2t to the 1/2 minus, plug in the bottom one, is just 2. And of course, clearly, when you plug in infinity to this, you get, well, the square root of infinity is still infinity. So this is infinite. In other words, the integral and, moreover, the series by the integral test diverges. Perfect. So we're done with part 2. Now moving on to the next idea, p-series. P-series is a generalization of certain types of series that we've seen that we can actually handle by the integral test. And this is actually one of them. In this case, this is 1 over n to the 1/2. The previous example we saw before discussing these two was the series of 1 over n squared. So this actually categorizes a lot of those types of series. So what this says is that it converges when p is bigger than 1 and diverges when it's less than or equal to 1. So in fact, we'll actually take a look at the case when it's equal to 1. Notice this is just a harmonic series. that we've seen before. And if you remember the harmonic series from 11.2, we actually saw proof that it actually diverges. And, well, from the P series, it diverges right away. Because here the power of n is 1, and according to the P series, so by P series, this diverges. Which kind of goes to show that the P-series test is really a pretty powerful test, but you have to have the right type of series. Now, the reason why the P-series test works is because, again, it's basically a application of the integral test. Because 1 over x to the p are functions that are positive and decreasing between the intervals, well, 1 and infinity, or in the interval 1 to infinity, I should say. And their integrals converge and diverge exactly when p is bigger than 1 and less than or equal to 1, respectively. And again, we saw that idea with the p integral. I believe that's what I called it anyways. The book doesn't call it anything, but they do mention it in chapter 7.8. So again, that's all I want to say as far as the integral test goes. Now we're going to talk about estimates of sums. So we're not quite done with 11.3. In fact, we're not quite done with integrals at all. So we'll see still a good amount of integration in the rest of this video. And it's actually going to be pretty interesting, because now we'll finally be able to not find out what the exact value of a sum is, but we'll be able to approximate a sum to a good amount of accuracy using a little bit of our calculator, but it kind of goes a little beyond that. So let's take a look at that right now. All right, so here I say, suppose that f of x satisfies the requirements of the integral test, so meaning that it's positive and decreasing in the interval 1 to infinity, and also f of n is a sub n, and let s be the sum of the series 1 to infinity of, here I'm indexing by I instead of n like usual, so I hope that's okay. So in doing this, by the way, I'm basically saying that we're assuming that the series is convergent. So that's kind of what we hope for anyways. Otherwise, there's no point in estimating the sum, because might as well just say it's a large number because it would go to infinity, or it may not exist. Anyways, we're also going to let s sub n be the nth partial sum of the series. And then I go on to say the remainder, r sub n, is defined to be the difference between s and s sub n. That makes sense. So whatever the series converges to, if you take the difference between that and any partial sum, that's the remainder up to that amount of terms, basically. So really it's a sub n plus a sub n plus 1 plus a sub n plus 2, and on and on and on. And you can think more about that if you like. In fact, I'm realizing now that if we're taking away a sub 1 or a sub n from the infinite series, actually the sum actually starts at n plus 1. So I misspoke there, actually. It should start at n plus 1, n plus 2, and so on. Okay. And the remainder actually satisfies the following inequality. I'm going to box this. So here, let me read. It says r sub n is in between these two integrals. One goes from n plus 1 to infinity of f of x dx. The other one goes from, so the larger one actually, goes from n to infinity. And this actually comes from the Riemann sum we saw previously. I showed in one of the examples. I believe I even shaded those rectangles for us. And that's where these actually come from. This is, by the way, known as the remainder estimate for the integral test. So now we're going to see if we can apply this. So for this example here, I don't know why I labeled it as A. Well, I labeled it as A because there's a follow-up question to this that I'm going to do the next screen. I don't have space for it. But for right now, for this example, we want to approximate the sum from n equals 1 to infinity of 1 over n cubed with the sum of the first 10 terms. So we're just basically going to plug in 1 through 10, add those together with our calculator, see what we get approximately. And then we're going to estimate the error of the approximation. So yeah, we can't actually find out the remainder legitimately because we don't know what the sum of this series is. But we can approximate the remainder, and approximating the remainder is essentially estimating the error of our approximation. So we're going to get that s sub 10, by the way, is the sum from n equals 1 to 10 of 1 over n cubed. This is just 1 over 1 cubed, which is 1, plus 1 over 2 cubed, plus 1 over 3 cubed, and all the way to 1 over 10 cubed. So it's not too bad. In fact, if you're daring enough, you can possibly do this by hand. I wouldn't dare do that live. That's going to take way too long. I'm just going to use my calculator like a normal person, I guess. But if you want to be crazy, be crazy. I encourage that. So let's see what we get using our calculator. All right, so I got about 1.1975. In fact, I want to explain, there's a really nice feature of the TI-83 Plus, or any TI beyond that actually, that allows you to figure out these sums pretty quickly. And it is sequence and sum. So the way I did this, again, using the calculator, is I took the sum of the sequence of 1 over x cubed, comma x, comma 1 to 10, close parentheses twice. Now how you get to these functions, there's a few ways, but the way I know is to go to list, which is second stat. Then you scroll over to math, that's sum. And then if you scroll over to the one before math, which is the middle column under lists, I believe it's operations, or OPS, I think for short. And then you just do this. So again, what these are the general term for a sequence, the variable of the sequence. In this case, it's really n, but I'm using x just because it's easier in the calculator. And then the initial term of the sequence and the final index, finally, of the sequence. And then if you do it without sum, it just lists it out in braces. But if you do it with sum, then it actually adds those together. So it's kind of neat to know you can do that with your calculator. And it saves a little bit of time too. All right, so this is our approximation using the first 10 terms. Now to estimate the error of the approximation, what we're going to do is, well, we're going to say that r sub n, our remainder, is going to be within these two integrals. So the integral from 10 to infinity of 1 over x cubed dx, and the integral from 11 to infinity of 1 over x cubed dx. And I thought I would have a little bit of space. I think we actually do kind of have space here. That's fine. I'll calculate both of these. They're actually pretty similar. The only difference notice is just the bottom limit. So in fact, let me just work with the right one first, and then from there we can actually calculate the left one. So here, the antiderivative of x to the negative 3 is x to the negative 2 over negative 2. So it's negative 1 over 2x squared, basically. Okay, good. And then we're evaluating this between, well, 10 and infinity. Now, when you plug in infinity, of course, the limit as t goes to infinity of 1 over 2t squared is just 0, because the denominator gets larger and larger. So this is really going to be 0 minus this evaluated at 10. Since it's negative, in total we have actually a positive value, 1 over 2 times 10 squared. And in fact, very, very similarly, this one will be 1 over 2 times 11 squared. With the exact same logic, if that makes sense. So now we can actually approximate these to see where our remainder is in between, and that'll be the error of our approximation. In fact, really we can just use the larger one, so we can say we're within that many decimals, basically. So I know 1 over 10 squared is 0.01, and I know 1/2 is 0.5. So if you multiply those, you get 0.05, or is it 0.05? I guess it's 0.05. So we know r sub n is actually in between. Well, 0.005 will be the upper bound. The lower bound will just be whatever this is. So I'm going to use my calculator for that right now. Yeah, so for the lower bound, I got 0.004 approximately. So the remainder is in between these two. So we're basically 3 decimal places of accuracy, more or less. In fact, there I think is a better way to calculate how many decimals accurate we are. So this just tells us what the remainder is. So the remainder is this far off. So it's somewhere in between 0.004 and 0.005. So yeah, this isn't quite super accurate then, but it's actually pretty good. So 1.19 is actually not too bad of accuracy. In fact, if you kind of consider the midpoint between these two would be 0.0045, and if you add 0.0045 to this, you get an estimation, probably a better estimation actually, of this series. And you'll see that if you add 5 to, so 0, 0, 4, 5, so if you add 4, 5 to 7, 5, it bumps this up, and it'll actually be like 1.2 in the end, I think. But anyways, I'm going to ask that follow-up question now to this example, so let's take a look at that right now. All right, so here finally the follow-up question to the previous example. How many terms are required to approximate the same series 1 over n cubed from 1 to infinity within an error of 0.005, so 1 order of magnitude more accurate than the previous error we got. So what we're going to do is we're going to take a look at the upper bound of the estimate, the remainder estimate, and by the way, I've written it here actually. So the upper bound was this. So if we consider the upper bound, which in this case is the integral from n to infinity of 1 over x cubed dx, because that's our f of x in this case, we actually saw what this was. Remember, the antiderivative of 1 over x cubed was 1 over 2x squared, what was negative 1 over 2x squared, like that. And when we evaluated this between n and infinity, well, we got 0 for plugging in infinity, minus negative this gave this sign to be positive actually, and then plugging in n just gave us this actually. So I'm going to erase this a little bit. All right, so fixing that up, we actually get this for the upper bound. And we want this to be, well, we want it to be less than 0.005. So really what we can do, 0.005 I meant to say. So now what we can do here is we can actually solve for n, and we'll have to actually, round up basically, but this will give us how many terms we would need in order to be within that many decimal places of accuracy. So if we actually reciprocate both sides of the inequality, we get 2n squared is bigger than the reciprocal of this. By the way, this is 5 over 1 with how many zeros? Well, let's see. If it was 1,000, then you move the decimal place to the left 3 times, and that will just leave you with 2 zeros in front of the 5. So it's actually 5 over 10,000. So if you flip that, that's 10,000 over 5. And then if you divide both sides by 2, really we're multiplying this side by 1/2. And that's nice because those amount to 10. So we just get a cancellation of one of the zeros. So n squared must be bigger than 1,000. So that means n must be bigger than the square root of 1,000. The square root of 1,000 is approximately, I think, 31.6. I just remember the square root of 10 is about 3.16. Don't ask me why I remember that, but I remember that. So that means n, if we're to round up, should be about 32 terms. So you need about 32 terms to be within this error of accuracy, which is kind of cool that we can actually do that, so we can get a really good idea as far as what this sum actually is. In fact, we'll go a little beyond with the next idea here. So, and I know this video is getting kind of long, but this is the last thing we're going to see, believe me, for 11.3. So from the remainder estimate, this inequality, we saw this previously, Rn is in between these two integrals. Adding Sn throughout the inequality will give the following. Well, the outer terms will just be Sn plus this integral, and I'll leave the middle one. The right bound will be Sn plus that integral to infinity of f of x dx. Good. And now what is the middle? Well, remember, r sub n was what? Let me use a different color here. R sub n, if you don't remember, was defined to be s minus s sub n. So notice when you add s sub n to that, they cancel out and you just get s. So in reality, this here is very useful for not finding the remainder, but this will actually give you the estimate of the sum itself. In fact, if you look back to the previous example we saw, with s being equal to the series n equals 1 to infinity of 1 over n cubed, well, these integrals, we actually evaluated them. What we ended up getting was, I'm trying to think what S10 was. So S10, I believe, was 1.1975. Okay, And the integrals were 1 over 2 times that number squared. In fact, we kind of see that right here. It's this guy. So actually, our sum, S, is in between those two things. It's in between 1.1975, there we go, plus this lower limit, which was 1 over 2 times 11 squared, which, by the way, that was 0.004. But, yeah, I'll actually approximate it better right now. And 1.1975 plus 1 over 2 times 10 squared. And that was legitimately 0.005. This I rounded a little bit. So I'm actually going to use my calculator to approximate each of these, and then we'll get a really, really good idea as far as what S is. Right, so here we go. So I've actually plugged each side of these into the calculator, and I got that S, the actual sum of the series, is in between these two values. And in fact, if you take the midpoint here, you get that the sum from n equals 1 to infinity of 1 over n cubed is about 1.2021. So that's actually within 0.0005 decimals of accuracy, believe it or not. But yeah, that's all I'm going to say as far as 11.3 goes. It was a nice application of the integral test to find an actual estimate of a sum of a series. And of course, I only did one example. In fact, this is something usually is not tested on. So maybe I should have said that at the very beginning, but it's definitely very, very interesting material. And it'll allow us to use our calculator, but actually go a little beyond the calculator and have the understanding that integrals are super helpful, because integrals are very much intimately related with series, but for whatever reason, integrals are easier to compute because we're just anti-deriving and there's only two terms we have to subtract. The only real issue with integrals, though, is that not every integrand is anti-differentiable. So that's something to keep in mind. Not every integral actually exists. But anyways, that's all I wanted to say for 11.3. Thanks for sticking around. Thanks for watching. Hope you enjoyed. See you in the next video for 11.4. See you then.